I'm Anil Kumar sharing with you some test questions on logarithmic functions. We'll actually have two parts in this particular video. In the first part, we'll discuss about logarithmic functions, evaluate some of them, use their rules and laws. In part 2, we'll take up applications. This video is for all the students who want to prepare for university, for pre-calculus, Cambridge O-level, IB. So many students will find it very useful. I hope solving these 14 questions will help them to prepare for their own test and they can really get almost 90% marks. So here are a few questions. I'd like you to pause the video, copy these questions. Question 1, 2, 3 and 4 are, I think, visible at present. You may copy them and then I'll move the test paper so that you could copy question number 5, 6 and 7. In this page, we have basic logarithmic functions where most questions can be answered without change of base. Question number 8, 9, 10 and 11. Now these questions need the understanding of change of base formula to solve. So you can copy these. We'll take them all one by one. The last three questions here are level 2 questions, they're slightly difficult. I'd like you to try them out and then look into my solutions. Now bridging the gap between change of base formula, as some students really have not learned change of base so far. For them, they might be getting ready for a quiz on logarithmic functions. I've taken up here an additional question, which is, can log to the base 3 of 4 plus log to the base 2 of 9 be expressed as a single logarithm using any of the laws of logarithms? So when we talk about laws of logarithm, we are looking into the product law, the quotient law, and the power law. So when I say product law, it really means log to the base of something of x and y could be written as log to the base, same base, as their sum, right? So that is the product law. The quotient law is log to the base of x over y will be written as log to the base of x minus log to the base of y. And the power law can be written as log to the base of a, x to the power of r equals to r times log to the base of a of x. I find it useful to repeat this before we take up the test, since on YouTube many of my viewers might have forgotten about logarithmic functions, and that will help them to understand and even solve the whole test paper, right? So now let's look into the function given to us, which is log to the base 3 of 4 plus log to the base of 2 of 9. As you can see, the base is different, right? So we can write that since the base is different, we cannot apply laws of logarithm. Laws of logarithm. Is it okay? Since base is different, you see the base is same, only then you can apply these laws. But here there is a key which some of you might know at this stage. That is, we could actually change the base. Once you change the base, then you can apply. So change of base formula is that if I have log to the base of, let's say, a of x, And if I want to change that to the base b, then we write this as a ratio of log base b to the x divided by log b of a, right? So change of base can help us write this expression as a single log, right? So now with brief introduction to laws of logarithms and change of base formula, let us make an attempt to complete this test paper. It should not take more than an hour to do this. Question number 1. Evaluate log to the base 2 of 512 cube, log to the base 4 of 1 over 64, log of 0.001, and 2 log 8 plus log 9 minus log 36. So the idea here is to write the logarithm when we know the base, the argument with the same base. So 512 can be written as 2 to the power of 9, right? So 512 can be written as 2 to the power of 9 cube of this, right? You should remember that 2 to the power of 10 is 1024, kind of kilobytes, right? So that is easy to remember, and half of this is 512. Okay, so that gives you log to the base of 2 of 2 to the power of 9 times 3, 27, and that gives you the value of 27 using the power rule, correct, which we just introduced. So that's the answer. Here, how can we write 64 as power of 4? We could always write this as log to the base 4. 4 to the power of 4 cube is 64, so minus 3. So the value will be minus 3. When we do not write any base, it means that the base is 10. So we have to write 0.001 as 10 to the power of something, which is minus 3. And therefore, we get the answer as minus 3 in this case. Here, we can first apply the power rule, rewrite the expression as log 8 squared plus log 9 minus log of 36. 8 squared is 64, so we get log of 64 plus log of 9 minus log of 36. And then we can use the laws of logarithms. Whenever it is plus, it gets multiplied. So you get log of 64 times 9 divided by 36, correct? So you could simplify this. 9 goes 4 times. And then you can divide this. 4 times 1, 24 is 16. So we get our answer as equals to 16. Is that correct? So that is how you'll do question number 1. Question number 2. Solve for x, log to the base x. Let me rewrite. Log to the base x of 9 equals to 2 over 3. The strategy here is to write it in exponential form. So we'll change the form here. We'll write it in exponential form. So that is to say, I will write this as 9 is equal to what? 9 is equals to x to the power of 2 over 3. So the base remains same. See, base is x, and that becomes the exponent. Right? 9 is equals to this. And now from here, you can calculate what x is, right? So it is to the power of 2 over 3. So we can write x is equals to 9 to the power of 3 over 2. Is it okay? 9 to the power of 3 over 2. And that is to say, basically, 9 square root, and then we cube it, right? Square root of 9, as you know, is 3, and cube of 3 is 27. So the answer is x equals to 27. Is that clear? Question number 3. Write each as single logarithm. We got half. So we'll use the laws of logarithm here. So first is the power law. We can write this as log to the base 4 of 16 to the power of half. Let me write square root here. Plus we have log to the base 4 of x cubed. Now square root of 16 is 4. So we get here log to the base 4. Square root of 16 is 4. Plus log to the base 4 of x cubed. Now if you are using as you have to write like a single log, right? So at this stage we'll use the properties of logarithms and then just multiply 4. So log to the base 4 of, multiply these, we get 4x cubed. So I did not really evaluate this. I could have written this as 1 plus that. Since we want to write as a single logarithm, we are actually placing it in this fashion. So I hope that step is clear, right? Now let's take up the next example, which is log to the base 2 of x squared minus log to the base 2 of xy plus log to the base 2 of y squared. So let's combine them in one step. We get log, same base 2. So these two quantities will be multiplied and we have to divide by xy. So what we get here is x squared times y squared divided by xy, which could be written as log to the base 2 of xy. Is that okay? So that is single logarithm for the given expression. Okay. So now let's take question number 4. Write 3 coordinates for each function. Y equals to 5 to the power of x, y equals to log to the base 5 of x. So what I will do here is make a table. We'll write just 3 coordinates. So we have to take 3 different x values and then write the coordinates. In logarithms, it is very important to understand that the good values to take are -1, 0 and 1. These are standard and the best values to take. So if I substitute -1 here, the y value will be y to the power of -1. If I substitute 0, I get y to the power of 0. And if I substitute 1, I get y 5 to the power of 1. As you know, this is 1 over 5, right? So this is 1 over 5. Anything to the power of 0 is 1. Anything to the power of 1 is the base itself. So that gives us the coordinate points x and y, which we can write as -1, 1 over 5, 0, 1, and 1, 5. Is that clear? Now, you could use the same strategy to make a table here for y equals to log to the base 5 of x, correct? So again, we will just create our table, find x, y, and write the coordinate points. Is that clear, right? Now, you know this is inverse of that function, right? So therefore, what do we expect here? So let me do the reverse. When we say inverse function, we are expecting these values here. They swap, right? So we are expecting these values here. So what I will like you to do is to test it out. That is to say, when you plug in this expression the value of 1 over 5 for x, what do you get for y, right? You will get as -1. So I kind of have done the reverse way, only to show you that these are inverse functions, right? So important thing to understand is these are inverse functions. Is that clear, right? So this exercise helps you understand that concept. Now let's take up how to sketch logarithmic functions. Now these questions are arranged in a way that you could review all your concepts. Now there have been other requests for how to sketch graphs for logarithmic functions. Therefore, I'll kind of go into details of this particular question. Now, we are going to use transformation of points to really sketch the function. I could rewrite this function as y equals to 4 log. We should actually factor 2. If you do that, you get x plus 1 plus 3. Now it is clear that if on the base, which is log to the base 10x, we have a coordinate point xy, then the transformation will be the x values will be multiplied by half, horizontally compressed by a factor of half, and move 1 unit left, so -1. That is how the x values will change. The y values will get vertically stretched by a factor of 4. So these y values will get multiplied by 4 and then you add 3 to it. Is that clear? So that is the transformation, right? Now if you look into log to the base, we have log to the base log x, which is base 10, right? And this is that function, which is 4 log of 2 x plus 1 plus 3, right? Okay. So for the basic function, when x approaches 0 from the positive side, y approaches negative infinity. Perfect. Then we consider 3 points where the x values are, when the base is 10, we'll take x values as 1 over 10, correct? We'll take as 1 and 10. For 1 over 10, the value is going to be minus 1. For 1, it is going to be 0, and for 10, it is going to be 1, correct? So these are 3 key values which you should always consider. And the fifth characteristic is when x approaches infinity, y approaches infinity. So in a way, that gives you 5 points. Now, very important point also is y-intercept. So you could find y-intercept also for your graph, right? Since it is moved, we'll find y-intercept later. So that is basic calculation where we'll just substitute 0 here. So let's do these points. So for the first one, when x approaches 0, 0 multiplied by half is 0, minus 1, that changes to x approaches minus 1 from the positive side, y approaches, now negative infinity times anything will give us negative infinity. Is that clear? So on a graph, it will look like something like this. So we're just using very rough sketches, which always make sense. So that is the vertical asymptote. So let me just draw a vertical asymptote here to represent this point. So this is the vertical asymptote at x equals to minus 1, correct? So that really means that when you're approaching, this is how the graph approaches, correct? Now the second point here, if I substitute point 1 over 10 is like, you understand, point 1, right? So point 1 here, half of point 1 is 0.05, minus 1 will give us 0.95. The y value, minus 4 plus 3 will give us minus 1. You can use calculator. So half of 1 is 0.5, and that gives us minus, this is minus, I forgot to write minus here, right? And minus 0.5 will give us 3. For 10, we'll get the x value, half of 10 is 5, that means 4, and 4 plus 1, 3, 7. When x approaches infinity, y also approaches infinity. That's the end behavior, right? So what you get here is a graph which will be kind of like this. Okay, so that is the kind of graph where we say one of these points here is 4, 7. Okay, and we have, let's say this point is 0.95. Okay, let me just say this is minus 1, this is at minus 0.5, and at minus 0.5 we have a value which is, let's say, 3, right? So this is 3 for us. We can actually calculate y-intercept. So let's do that. Okay, so let's do that here. So we'll calculate y-intercept. So we say y-intercept means x equals to 0 in this particular expression. So we get y equals to 4 log of 2 times 0 plus 1 plus 3. So let's calculate. What do we get? So we have 4 log of, so basically 2, right? and then we'll add 3 to this. We get 4.2 as our answer. This is 4.2. So the y-intercept is 4.2. Is that clear? So you could get y-intercept. You could also find x-intercept, right? You can treat this as minus y equals to 0 and calculate x-intercept also. So let me write here x-intercept for you to calculate. Is it okay? So I'm just leaving it. Fine, not a bad idea. You just equate this to 0, bring this here, divide, and then get your result. Anyway, now let's get back to, but this is fairly good graph. We could write x and y, 0 here. Okay. So that is a vertical asymptote. So let me write down the characteristics one by one. So let's see. The characteristics, let's start with domain. What is the domain of the function? So domain is x belongs to real numbers where x is greater than minus 1. So that is minus 1, and this is a vertical asymptote. The range, as you know, for logarithmic function is always all real numbers. Now we have a vertical asymptote at x equals to minus 1, right? So those could be good, this thing, and then we can say end behavior. When x approaches negative 1 from the positive side, y approaches negative infinity. When x approaches infinity, y approaches infinity, right? And you could say always increasing. Is it okay? So those are good characteristics to mention. So I hope that makes sense. So let's move on and take up the next question now. Question number 6. Explain why logarithms for negative numbers do not exist. Now that brings us back to basics, right? Now this communication question is introduced here only to connect exponential and logarithmic functions, right? So what you learned earlier, that if you have function y equals to some base to the power of x, then that exponential function could be graphed kind of like this. Correct? Now, in this particular function, what we notice here is that the domain is x belongs to real numbers, right? And the range is y belongs to real numbers where y is greater than 0. Is that okay? So y is always greater than 0. Now what are logarithms? Now logarithms are inverse of exponential functions, correct? So basically what you notice here is that the inverse means the y value is never negative. See, since y value is always positive, what you notice here that for logarithms the domain and range swap. So for logarithms the domain becomes what? So the domain x now belongs to real numbers where x is greater than 0, and as far as the range is concerned, it switches and we say y belongs to real numbers. Is it okay? So what we get here is a logarithmic function which is kind of like this. Do you see that? So exponential functions and logarithmic functions are related with inverse, correct? So y equals to x, reflection gives you the log function. Now explain why logarithms for negative numbers do not exist. Simply because there is no exponent which will give you a negative result, right? So you could also say that exponent of any non-negative number right, is never negative. Is it okay? So exponent of any number is never negative, and therefore, so the base, basically base is, so in this case, let me write here, base is greater than 0, base is not equal to 1, and that is the restriction here on the base, correct? So base, we say, when we say exponent of any non-negative number, that is to say, we're looking into the value b, right? Non-negative number b, right? Is never negative, it's always positive. Do you get an idea? And therefore, we cannot have the logarithms of negative numbers. So that could be an explanation for the given question. Right. So let's move on and take up question number 7, which is, use calculator to evaluate log to the base 5 of 20 correct to 3 decimal places. So now we have to calculate log to the base 5 of 20 using calculator. Now that brings us to the second part of this test, which involves change of base formula. So let's understand change of base formula and then move on. So if I have base A, for example, and if I want to change this base to B, I could write this as log to the base B of x divided by log to the base B of A. That helps. Now on the calculator, you could have base 10 or base E, which is ln. Let's change it to base 10. So we could write this as log to the base 10 of 20, right, divided by log to the base 10 of 5. So once you do that, then you can use calculator and find the answer, correct? So let's now evaluate. So important step is to change the base. So we have log, so base 10 is by default, correct, of 20, and then we'll divide this by log of 5. So we get our answer as 1.86135, which we can round to 3 decimal places. So it could be written as 1.861, correct? So that is how you use it. Now we are going to extensively use change of base formula from here onwards till question number 14, okay? So let's move on. Here we have question number 8. We need to evaluate 2 log to the base 3 of x minus half log to the base 3 of 64 plus log 2 of log 3. Let's rewrite this. So we have 2 log to the base 3 of x minus half log to the base 3 of 64 plus log of 2 divided by log of 3. Now in this particular case, you clearly see that the bases are different, right? So we have to apply change of base formula. And you should change the base to 3. So change base to 3 for log of 2 and log of 3. Do you see that? So let's do this part separately, and then we'll incorporate and then evaluate. Is that okay? So see, log 2 could be written as, we're changing the base to 3, could be written as log to the base 3 of 2 divided by log to the base 3 of 10, because 10 is the base here. Similarly, log of 3 could be written as log to the base 3 of 3 over log to the base 3 of 10. Correct? So log 3 of 3 basically is 1, correct? And log 3 of 10 will cancel when you divide this by the other. So taking that into consideration, let's continue. So we have equal to log 3 of x square, we applied the power rule here, minus log 3 of square root of 64, let me write 64 to the power of half, plus log 2, I'm writing as log to the base 3 of 2 divided by log to the base 3 of 10 over log 3 is log to the base 3 of 3 divided by log to the base 3 of 10. So log to the base 3 cancel out. Perfect. So we can cancel these base terms. So what do we get here? So what we get here basically, and log 3 of 3 is 1. You know, log 3 of 3 is equal to 1. So this becomes 1. So we get here log 3 x square minus log 3. Square root of 64 is 8 plus log 3 of 2. Since this is 1, right? If you want, you can write 1 here. Now you can apply the power rules and you could write this as log 3 of x square times 2, right? So we should write, they get multiplied. So 2x square minus means divide by 8, correct? So that's what you get, which could be written as log to the base 3 of x square over 4. Is that clear? So that is how you would actually evaluate this particular sum. I think the question should have been not to evaluate but to write as single log, right? So simplify. Okay. So let's move on and do the next question. Question number 9. Question number 9. Show that 3 over log to the base 2 of a minus 4 over log to the base 4 of a equals to minus 5 over log 2 of a. Let me rewrite the question here. It's 3 over log to the base 2 of a minus 4 over log to the base 4 of a equals to minus 5 over log to the base 2 of a. Now you are seeing reciprocal of logs here. How do we solve such a question? Now here I'll remind you of log to the base, change of base formula. Let's get back to change of base formula. So if I have, let's say log, let me take any one of them, log 2 of a, let's say we have log 2 of a, right? So if I change the base to a, then what happens? See what happens. I could write this as log to the base a of a divided by log to the base a of 2. Now a of a is 1, so I could write this as 1 over log to the base a of 2. So it becomes reciprocal. Do you see that? Do you see that? So it becomes a reciprocal of logarithm. So when you swap base and the argument, you could write this as 1 over. Do you see that? So using this property or the rule, what we can do here is we could write this as 3 times log to the base a of 2. Do you get it? Right? So 1 over that, it goes into the numerator. Similarly, I could write this as minus 4 log to the base a of 4. And the right side becomes minus 5 log to the base a of 2. So now I think it becomes much simpler, right? So let's do the left side. So we have log to the base a of 2 cube minus log to the base a of 4 to the power of 4. 2 cube is 8, so we get log a of 8 minus log a of 4 to the power of 4, which is 16 times 16. Let me write 16 times 16 here. Right? We are not using calculator at present. So log to the base a of 8 divided by 16 times 16, which is log to the base a of 1 over 32, right? Since 8 could go 2 times, correct? 2 times 16 is 32. Now 32 can be written as log to the base a of 2 to the power of minus 5, and that is minus 5 log to the base a of 2, which is the right side. Does make sense, right? So the right side is the same as the left side. Do you see that? So that is how you could prove it. Perfect. Question number 10. Show that log to the base a of 1 over x equals to log to the base of 1 over a x. So let's do the left side first, which is log to the base a of 1 over x. I could write this as log to the base a of x to the power of minus 1. Using power rules, we can write this as minus log to the base a of x, right? Now, that is the left side. Now, let's look into the right side. On the right side, I have log to the base of 1 over a of x. We could change the base, right? Let's change base to a. So I could write this as log to the base a of x divided by log to the base a of 1 over a, correct? So that is log to the base of x divided by log to the base a of a to the power of minus 1. That gives us log to the base of x over, using power rule, we get minus log a of a, which is minus 1. And that is equals to minus log of x, correct? Since we know, let me just complete one more step here. We could, log of a to the base x of minus 1, correct? So log to the base a. So what you notice here, that if you change the base, you can easily show that left side is equals to right side, correct? Which is same as left side. So that is how you would actually prove that the reciprocal of the base and the reciprocal of arguments, they're somehow connected as shown. Let's take question number 11. Question number 11. Evaluate log to the base of 0.25 of log to the base 2 log 10 to the power of 16. Let's rewrite the question. 0.25 is 1 over 4. And what we have here is log to the base 2 of log 10 to the power of 16. Now here the base is 10, right? So the inside part of this expression can be written as 16 using the power rule. So we have log 1 over 4 log to the base 2, and this is power rule, right? So it's a 16. So I could write this as log 2 of 16, correct? Now 16 can be written as 2 to the power of 4. So we could write this as log 1 over 4 log 2 times this is 2 to the power of 4, correct? Applying the power rule, we get this as 4. So I could write this as log 1 over 4 of 4, correct? Now 4, since the base is 1 over 4, can be written as log to the base 1 over 4 of 4 to the power of minus 1, or what I'm trying to say is 1 over 4 to the power of minus 1, right? So I'm writing this as log 1 over 4 of 1 over 4 to the power of minus 1. That is same as 4, correct? So this is using the power rule minus 1. So we get this expression as minus 1. So I hope that is clear. Few more questions to go. Question number 12. We need to solve log x to the power of log x equals to 4. Let's rewrite log of x and x to the power of log of x, it is, right, equals to 4. Applying the power rule, I could write this as log of x times log of x equals to 4, which is log of x whole square, which is 4. Now you could square root this, so you get log of x equals to square root of 4. Whenever you square root, you do plus and minus. So we get two possible solutions, that is log of x is equal to plus 2 or minus 2, correct? So we'll take them individually. So we have one as log of x equals to minus 2, the other one as log of x equals to plus 2. Now that means x is equals to 10 to the power of minus 2, which is 1 over 100. And this means x is equals to 10 to the power of 2, which is 100. And therefore, we get two solutions. One is x equals to 1 over 100. The other one is 100. Question number 13. If a square plus b square equals to 14ab, where a is greater than 0, a not equal to 1, x greater than 0, prove that log of a plus b over 4 equals to half of log a plus log b. Now in such questions, let us see what we need to prove. So we need to prove that log of a plus b over 4 is equal to half of log a plus log b. Correct. Let's see the right side. We'll apply the laws of logarithms. We could write this as half of log ab, product rule, right? So that means we could write this as log of square root ab. Now that basically means that we have to prove, from here we can say we have to prove that a plus b over 4 is equals to square root of ab. Does it make sense? A plus b over 4 equals to square root of ab, right? That is what we need to prove. So let us see what we are given and then we'll prove this. We are given a square plus b square equals to 14ab. Now we could use a plus b whole square formula, which has 2ab. So what I will do here is, we could rewrite this as a square plus b square plus 2ab equals to 14ab plus 2ab. So I've added 2ab on both the sides. That helps me to make the left side as a perfect square. We could write this as a plus b whole square. The right side becomes 16ab. Now when I square root, what do I get? Okay, let me take it to the right side. So if I square root, I get a plus b equals to square root of 16ab, which is 4 square root ab is a plus b, or a plus b divided by 4 is equals to square root of ab. Correct? So we have shown that a plus b divided by 4 is indeed equals to square root of ab. Correct? So that is how you could prove. You could actually start from here, go all the way, take log both sides, and get to this also. So that is an alternate method. So I hope both the steps are absolutely clear. Okay. So the next example will follow the approach which I showed you, the alternate approach. Question number 14, which is the last question. If a cube minus b cube is 3a square b plus 5ab square, where a is greater than 0, not equal to 1, x greater than 0, prove that log a minus b over 2 is 1/3 of log a plus 2 log b. So we will now prove this particular thing. Now as I said, we'll begin with the known fact, which is, what is a cube, a minus b whole cube equal to? A minus b whole cube, that's a formula, right? So we could use this as a cube minus 3 a square b plus 3 ab square plus b cube, correct? Now we can rearrange. We get a cube, this is minus b cube minus 3 a square b plus 3 ab square. Now we are given this, that is a cube minus b cube is all that. So I'm going to replace this by 3a square b plus 5ab square. So I could write this as 3a square b plus 5ab square, and we have here minus 3a square b plus 3ab square. We can simplify combining the like terms. So a square b with a square b and ab square terms will combine these. 3a square b minus 3a square b is 0. 5ab square plus this is 8ab square. So we get a minus b whole cube equals to 8ab square. So that is a minus b whole cube, correct? So if I cube root, I get a minus b equals to cube root of 8ab square. Now cube root of 8 is 2, right? So this could be written as 2 cube root of ab square. Is it okay? So dividing by 2, I could write this as a minus b over 2 equals to cube root of ab square, right? Now if I take log both sides, what happens? That is what we will see, right? And that will give us the result. So let me expand it here. If I take log both sides, I could write this as log of a minus b divided by 2 equals to log of cube root of ab square. Now that gives us log of a minus b over 2. We already have the left side term. Cube root means 1/3 of log of ab square. Let's apply the laws of logarithms, and we could write this, 1/3 because the cube root. We could write this as log of a plus log of b square. Applying power rule, I could write this as 1/3 log of a plus 2 log of b. That's what we need to prove, correct? Hence proved. So I hope the proof is straightforward. So the idea here is that you could start with the basic formula, substitute what is given, and derive what you need to prove. You would adopt this approach in question number 13 also. I hope you appreciate and like the solutions which we have provided, and these questions which we picked up from previous test papers will definitely help you to prepare for your own test. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'll be great. Thanks for watching and all the best.